Hello computer science students, welcome back. In this video we're going to prepare our first meaningful assembly program, and we're going to test it and figure out, make sure it works and go through some logic here. So far we've talked about how do we return a value, how do we add values, how do we debug, how do we write a loop, but we haven't really solved any problems. This is our first problem solving video. And so the problem we're going to solve is, can we calculate n factorial? So let's pull up a sheet and talk about the problem first, make sure we're all on the same page before we start coding. So we want to calculate n factorial. Right, so let's say that, just as an example, 5 factorial equals 5 times 4 times 3 times 2 times 1. And so how do we want to write this? We want to be able to calculate this for any n. So that means n could be 5, it could be 100, could be 12, could be 3, who knows. And so what programming technique are we going to need? We're going to use a loop. Right? Anytime that you don't know how many times you're going to have to perform an action, you have to use a loop. So we don't know what n is going to be, we don't know how many times we have to perform this action, so we're going to need a loop for this. And so what could the loop do? Let's say that we had like a result variable, and let's say we start off with it equaling 1. Well, for 1 factorial is just 1, so we're done. 2 factorial, what would we need to do? It's 2 times 1, right? So we need, in this case, for 2 factorial, n equals 2, and result starts off equaling 1, because again, we're going to assume that result equals 1 is just something we do. So if result equals 1 and n equals 2, then what we need to do is make result equal result times n, right? Or result equals 1 times 2, result equals 2, and then we're done. Right? Let's walk through a couple more examples here. All right, let's say we did 3 factorial. So that would have to equal 3 times 2 times 1. So n equals 3. And now we're going to start seeing how the loop has to work. We start with result equals 1. Right? This is kind of our starting point. So how can we calculate this? What we could do is imagine that we really put the times 1 at the start. It doesn't really matter where we put the times 1 because it doesn't actually affect the result. But if we did, let's do result equals result times n, just like we started our last loop. That would mean that result equals 1 times 3. So result equals 3. So imagine that being one loop. If we wanted to loop again, all we have to do is say n equals n minus 1, and then loop again. Result equals result times n. That means result equals 3, because result is 3, times n, which is now 2, right? When n equals n minus 1, that means n equals 3 minus 1, which means that n equals 2. So result equals 3 times 2, result equals 6. And so you see the pattern here is that we're always taking result equals result times n, and then subtracting 1 from n, and then looping again until n eventually equals 1, and then we're done. Right? And so hopefully you see that this process will get us n factorial. So that's the concept behind what we're going to program. Now there are alternate solutions, there are ways to write this in other ways, but this will demonstrate a couple concepts that I want you guys to be aware of as well. So this is the process we're going to try to follow. Alright, so let's actually code. We're going to use the nano editor again. Let's call this factorial.s because it's an assembly file. We're going to start with our comment as usual. Oops. Again, the stars, the little individual stars here are not necessary, but I think it looks nice and shows you where the comment is much more clearly. So factorial.s calculates n factorial, and the author maybe, for me at least, is Ryan Matfeld, and for you guys it may be something different. Dot syntax unified dot global underscore start, and then we create our underscore start label, right? This should hopefully be starting to become second nature to you a little bit, or at least this process so far is the same as we've used for everything else. All right, so in our loop that we just walked through, what variables did we use frequently? We used the result variable and the end variable. So that's a sign that if we're going to use registers for variables here, that's what we want to do. We're going to need two registers, one for the result and one for the n. And since we want to return whatever n factorial is, as we ran this example, the n factorial result was always stored in the result variable. So really we want r0, our default return value, to be our result number. So let's start with that. Move r0, 1. So this means result equals 1. R0 is the result of our math. All right, now we need n, right? This is what factorial value we're going to use. So let's use r1 for that. We're going to move into r1. Let's start with 5 factorial, I suppose. So n equals 5. R1 is n. All right. So it's time to start running the algorithm we talked about. So that algorithm involves multiplying result by n, and then subtracting 1 from n and looping until n equals 1. Right? So that means we want a label to loop to. We'll call it our loop label. So the first thing we want to do in our loop is check, is n 1? Why do we check this first? Well, what if n was 1 to start with? If n equaled 1, then we're done. Like there's nothing to multiply by, right? The result is 1, so we're done. So let's check that. Compare r1 to the value 1. Compare n r1 to 1. And then if it is equal, you could also do less than or equal. Let's do equal though. If it's equal, then we want to jump to our exit or our end. Let's call it end. Sure. In fact, let's call it underscore end. Let's create a little mirror here. We have underscore start to start, underscore end will end. How about that? And so we will compare, sorry, I should say, if r1, if n, r1, is equal to 1, end. All right, well, what does end mean? Right now, nothing. That should be a label. So at some point, we're going to need to fill in this end label. This will break us out of our loop. One reason I'm writing the program this way is to show you there's multiple ways of writing loops in assembly. You can loop on a condition, or you can exit the loop on a condition. So the first loop we did, we looped on a specific condition. Now we're going to exit the loop on a specific condition. So this lets me show you a little bit more of assembly and give you more options when you're writing loops. All right, so we compare r1 to 1. If it is equal to 1, we end. If it's not, we keep going. One argument, there's an argument for using less than or equal in case they put in a negative number, and that's probably the correct way of doing it. To just say any negative number factorials is going to be 1. But let's, and so maybe if you do BLE, branch less than or equal to, that might even be a better solution. We'll stick with equal though, and just make sure that we only test positive numbers. And that'll be fine for our little assembly test here. But just thinking about it, that may be a problem if you try a negative number, because you'll cause an infinite loop. But regardless, let's continue on. So what do we do in our loop? We multiply our result by it. Well, we take result equals result times n. So that means we need to multiply r0 equals r0 times n, which is r1. So this is basically saying result equals result times n. Right? If R1 is n and R0 is result, then we're saying result equals result times n. So we multiply, then we subtract 1 from n. N is R1, so R1 equals R1 minus 1. So n equals n minus 1. And then this is going to be BAL, which means branch always. We are always going to jump back up to our loop. So when I talked about in the last loop we did, we looped on a condition, now we're breaking from the loop on a condition. This is what I mean. So this loop will always loop unless R1 equals 1, and then we stop. And you know what? I am going to go back and change this to BLE. We want to make sure this does handle negative numbers, and there's no reason not to. So if n is less than or equal to 1, we end. That way we prevent infinite loops. All right, so now we need to end. How do we end? Same way we've been doing it before. Register 7 gets the value 1. When we end, return an int. And we do SWI 0. So there's our program. Control X or escape X, Y to save, write the file name, we have factorial.s, and now we need to go through our assembly process. We assemble to an object file with the object file called factorial.o, and we're going to write factorial.s. Oh no, look at that, we have a problem. Uh-oh. Well, I think it's pretty clear here. A similar message is unrecognized syntax mode unfied. Whoops. Yeah, that was supposed to be unified, so that was a typo. These things happen. So syntax unfied, let's do unified. And start. All right, let's save this. RD and RM should be different in mul. Oh, the destination register and the multiplication register should be different. I did something wrong in mul. Let's take a look. Oh, right. So there's one quirk with mul that we need to keep in mind. If you're going to multiply a number, and the way that computers do multiply, this is actually a really good note, so I'm glad we ran into this. With the multiply command, if you're going to multiply a register as part of the multiplication, you can't store the result of that multiplication in the same register because of how the computer does the multiplication process. It uses the registers while it's multiplying. So if you write it this way, mul r0, comma r1, then that is saying the same thing. Result equals result times n. So it's just a little quirk with the mul command, and it's a good thing that I meant to mention and didn't. So this actually works out. So let's escape, Control X, save, and try this again. There we go. We finally have no issues. So that's a good little mini debugging session for you, which was clearly entirely planned, and I'm glad that you could all benefit from the excellent planning I had here. So we've now assembled and fixed our issues, and we're going to finally link from our object file. And then we could quickly test it and see if it runs. In general, I think debugging is probably better, but I think in this case it will work unless I made another mistake of some sort. How can we test? Run it and then see what the return value is. What is 5 factorial? 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. So we should get the result 120 here. Oh, we did. So that's a good sign. We computed 5 factorial and got that correct result. So this is a good sign, but if it didn't work, that's okay. We could look at the debugger. So let's try debugging real quick. See this as it runs. Again, I'm going to break at start. And let's see, we need to run, and then we're going to do layout reg or layout regs, whichever you prefer. And so now that we've run our program, now we can run. So we create the breakpoint, we run our program, then we switch to the regs layout so we can see how the registers are working in our program. If we look at it, we have our start label, with 2 commands, our loop label with 5, and our in label with 2. This all looks right. Let's do ni for next instruction. So our result starts as 1, n starts as 5. So let's jump into our loop. Is 5 less than or equal to 1? No. So we do not branch to our end label. Instead, we continue running. We're going to multiply. Notice that my command was mul r0, r1. And it has been filled in to say r0, r1, r0. Because this would be another proper way of writing it. This register here, r1, is altered as we go through the multiplication. So this is really what ends up being written when you do r0, r1. Just a quick little note there. But the long story short is we're going to multiply these two together and save the result in r0. So 5 times 1 is 5. We should see r0 up here change to 5 when I run this. Yep, and sure enough, there it goes. We're then going to subtract 1 from r1. So n is going to change from 5 to 4. Yep. And then we always loop, right? This is BAL, which means branch always, to our loop label. So we're going to branch all the way back up, compare r1 to 1, loop again. 5 times 4 is 20, 4 becomes a 3, loop again. 20 times 3 is 60, 3 minus 1 is 2, loop again. 60 times 2 is 120. Seeing our registers update up here. R1 changes to 1. We loop again. Now R1 is 1. There's no sense in multiplying by 1 again, so our loop is going to compare. 1 is less than or equal to 1, so we are going to branch to our end label. So if we watch our program tracker here, it should jump down to the end label. And sure enough, it does. So now we move R1 to R7, and we exit our program, and we're done. So we can quit this session. And we have successfully seen our factorial program running and working and solved this first problem, solving the factorial problem by writing a program that solves for any factorial up to the limit of the size of an integer, which is about 2 billion unsigned and 2 billion signed and 4 billion unsigned. So that should get you you should test this with more values, and that should get us through. If you have any questions, please let me know, and I will see you all next time.